Welcome back, everyone. Today's chemistry lesson is on subatomic particles. The purpose of today's lesson is to teach you about the basic subatomic particles of an atom, which are protons, neutrons, and electrons. Before we get started, I want you to stop and grab yourself a periodic table because what we're learning is based on the things you're going to see on the periodic table. So just looking at the numbers is really not going to help you. At the very end of the video, there's going to be some practice problems, and that's a great time for you to stop the video as well and make sure you understand what's going on. Let's try to start focusing here on one subatomic particle at a time. And I've color-coded them for you, so this should be pretty easy. We're going to start off with the green. You can see that these are the protons, and we're going to fill out this chart as we go, and this is just the basic information about these three subatomic particles. So like I said, this is the proton. You can see that protons are positively charged. We give it a +1 as its charge, and from what you saw in my picture a moment ago, the protons are located in the nucleus, right smack dab in the middle of the atom. We're going to give a proton a relative mass of 1. So you might be wondering, like, what in the world does that mean, a relative mass? A relative mass is just a comparison in size to other things. And so I'm going to be comparing the size of the proton, the neutron, and the electron. The real mass of a proton is incredibly tiny. We're talking 1.67 times 10 to the negative 24 grams. That's so tiny that we really don't talk about it much in chemistry class, and we prefer to compare the sizes of the protons, the neutrons, and electrons. Sometimes that relative mass of 1 is accompanied by a unit of AMU, and AMU stands for atomic mass unit. I like to think of it sort of like a fake unit. It's not something that you'd actually measure out in the classroom, but allows us just to compare the sizes of these particles. Okay, so now you see the blue neutrons being filled in, and you'll notice they're in the same location as the protons. That's right, they're right in the nucleus. So what else is important about this particle for you to know? The charge on a neutron, like its name suggests, neutron, neutral, is no charge at all. It has 0 charge on it. Like I said a moment ago, it is found in the nucleus, and it also has a relative mass of 1. So what that means is the proton and the neutron, for all our purposes, is the same size. You might be wondering, what's the purpose of a neutron if it has no charge to it? Well, the neutron is actually quite important in the nucleus. It's required for stability. If you think about it, what would happen if there were no neutrons? All the protons are positively charged. Well, positive charges repel each other. They would push outward and push away from each other, which would cause incredible instability in the nucleus of the atom. So I like to think about the neutron as a buffer. It's really helping the protons space themselves out a little bit, and it allows the repulsions to be minimized. Let's now move on to the electron. The electron is a particle that has a -1 charge. It is equal and opposite to the charge on a proton. As you can see from the visual, it is not found in the nucleus. It's found outside the nucleus. Here's something that's really interesting. The electron is incredibly tiny compared to the proton and the neutron. As you look at the relative mass, you'll see how tiny this particle is. Because of that, it really does not contribute to the overall mass of the atom. You'll see in a moment that the electron has nothing to do with the calculation for atomic mass. It's simply too tiny to make a difference. On this next slide, you're going to see a chart. As we look at this chart, I would like you to start looking for patterns. There's some important items here. On the left-hand side, you'll notice that I'm including some of the symbols of elements on the periodic table. You'll also notice that I've selected all neutral atoms. Atoms are all neutral until a chemical reaction occurs which changes the electrons, either adding electrons or removing electrons. Next to the column with the element symbols are two important things, atomic mass and atomic number. What I'd like you to figure out is, what are these things and how do they relate to protons, neutrons, and electrons? Let's start off with the atomic number. The atomic number is by far the most important item that we have on this chart. Why is that? Because the atomic number identifies the element. When we refer to element number 11, we are referring to Na, which is sodium. If we say element number 15, we are referring to element P, which is phosphorus. Now I've highlighted the atomic number for you. This is where I want you to stop and stare at the numbers and see if you can see any patterns emerging. One of the things that I'm hoping that you're noticing is that the atomic number is exactly the same as the column showing protons. This is really an important feature of the periodic table. The periodic table is organized by atomic number. It goes from the lowest atomic number to the highest atomic number. In other words, what we're really doing, the number one organizing factor on the periodic table is the number of protons. Why is this so important to you? Because you need to know that the one thing that you can always rely on for identifying an atom is looking at the number of protons that it has. In other words, an atom of Na, sodium, will always have 11 protons. An atom of fluorine will always have 9 protons. What we're going to learn in the upcoming slides is that neutrons and electrons might change, but the number of protons will always stay constant for a given element. Let's move on now to atomic mass. The same as we did before, I want you to look at the atomic mass column. Look at all the other numbers. Can you see a pattern emerging? In other words, what is atomic mass? Hopefully you're noticing that the atomic mass, or the mass number as we often call it, is made up of the protons and the neutrons added together. This makes sense because, as we mentioned earlier, the protons and the neutrons are much, much more massive than electrons in size. Electrons are so teeny-weeny they barely have anything to do with atomic mass. So it makes sense that when we calculate the atomic mass or mass number of an atom, we are taking the number of protons and adding it to the number of neutrons. Okay, let's go back to the protons again. At this point in time, I want you to stop and look at all the numbers on the chart again. Can you find any other patterns for me? Anything else that looks interesting related to protons on this chart? All right, so this is pretty cool. In a neutral atom, the number of protons and the electrons is always the same. This should make sense to you. If the atom is neutral, and that means it doesn't have a charge overall, the number of positive things should equal the number of negative things. In other words, for Na, there are 11 positives in the nucleus, and there are 11 negatively charged electrons spinning around doing something on the outside of the nucleus. When we add those two together, it adds up to 0. I've now switched over to a different chart. This is a chart showing you important information about ions. If you look over on the left-hand side, you'll notice something different compared to the last slide that I had. Ions are not neutral. They have charges. Some of them are positive, some of them are negative. We're going to look at the numbers again, and I want you to figure out what's going on here. Can you figure out what patterns are emerging? Let's start off with the basics. Same as the last slide that we looked at with atoms. The atomic number and the protons are identical for ions. As I mentioned before, protons are the most important thing for you to be looking at when you look at an individual element, because the protons will never, ever change. Even if you have a charge on that atom, you'll still have the number of protons. The other thing that has not changed is the atomic mass. The atomic mass is still made of the protons and the neutrons added together. So look a little closer now. Focus in on the charges. Let's pay attention to the first one, which is calcium +2. Look across the row. Where is the +2 coming from? Maybe you could even see something different than when we were looking at atoms. One of the columns looks suspiciously different than it did before. You got it. It's the electron column. Something's going on with the electron column. If you remember when we were looking at atoms, the protons and the electrons were always identical. And we said that made sense because atoms are neutral. Well, ions are not neutral. They have an overall charge. So here's what's going on. In a chemical reaction, the electrons can actually be lost and the electrons can actually be gained. So we can add negative things and we can lose negative things. It's important for you to remember, though, the protons never, ever, 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 ever change in a chemical reaction. Take a look at the protons that I've got shaded in green. So the calcium has 20 protons. And the calcium +2 ion, instead of showing us 20 electrons, look at what happened. It suddenly has changed to 18. Do you notice what happened here? 2 of the electrons are gone. Maybe they were given to another atom in a chemical reaction. All we know is 2 of them are no longer there. So how do we figure out what's going on with the charge and where does it actually come from? Let's take a closer look. If the protons all have a +1 charge, and in this particular ion there are 20 of them, that gives us a total charge in the nucleus of a +20. Now on the outside, we've got those 18 electrons, and we know that those are all negative. So 18 multiplied by -1 will give us a charge of -18. So look at the overall balance here. +20 from the protons, -18 from the electrons. That gives us an overall charge of +2, and there's the +2 charge that we see next to the symbol of the element. How about we try one more of these just for practice? If we take a look at the 4th one down, this is the atom fluorine, which has now changed to the ion fluoride. Atoms of fluorine have 9 protons and 9 electrons. But we notice the ion fluoride has 9 protons and, oh, look at that, 10 electrons. It's got 1 extra. It must have gained an electron in a chemical reaction. So, just breaking it down, where did the charge come from? 9 protons gives us a nucleus with a +9 nuclear charge. 10 electrons, each of them having a -1 charge, is a -10. Let's add these things together. +9 from the protons, -10 from the electrons. That's an overall charge of -1. And there we see the fluoride with a -1 charge. It's just that easy. Let's go on to our next topic here, which is how do I write the symbol for an atom? The symbol for an atom is a useful tool. It's a concise way that chemists show important information about the atom. Let's talk about the important aspects of it and where we put what. Let's try to get familiar with this. Here we go. I'm going to use an X just as a general term that we're going to say this could be any element symbol off the periodic table. In the upper left-hand corner, this is where we put the atomic mass, or what we sometimes call the mass number. Down low is where we put the atomic number. And if there is a charge, it would go in the upper right-hand corner. This is the point in time where you need to have a periodic table in front of you. If you don't have one, please go and find one and be looking at these numbers as we walk through examples. Otherwise, you won't get the most out of this tutorial. Written in red is some information for us. It says, write the symbol for an atom that has 11 protons, 12 neutrons, and 11 electrons. So let's just start this off with the 11 protons. As we mentioned before, the protons helps you identify the element. It's the only one of these three subatomic particles that will help you figure out what symbol, what element you have. So looking at your periodic table, you could look up 11 protons, which is an atomic number of 11. And you would find out that this element is sodium, or Na. That also means if you have 11 protons, that the atomic number should be going in the bottom left-hand corner as shown. Let's move on to the atomic mass. If this atom has 11 protons and 12 neutrons, we know that those two subatomic particles make up the atomic mass, or the mass number, which is put in the upper left-hand corner. 11 plus 12 gives us an atomic mass of 23. The last thing we want to look at is the overall charge on this atom. We can see that it has 11 protons and 11 electrons. That gives us a plus 11 for the nuclear charge and a negative 11 from the electrons on the outside. We also know that if you have the same number of protons and electrons, the atom will be neutral. Therefore, we would not put anything in the upper right-hand corner of this symbol. This time we have 35 protons, 46 neutrons, and 36 electrons. 35 protons tells you right away what the element is that we're looking at. This happens to be bromine. We also can put the 35 down low because that's the atomic number. Let's do the atomic mass in the upper left-hand corner. We'll take our protons, let's add them to our neutrons, and that gives us an overall total of 81. Therefore, we put an 81 in the upper left-hand corner. This time we have 35 protons, or a nuclear charge of plus 35, but there are 36 electrons circling on the outside. Positive 35, negative 36, that adds up to a charge of negative 1, which goes in the upper right-hand corner of the ion. At this point in time, I'd like to take a closer look at the periodic table. Specifically, let's take a look at the element that we just saw one moment ago. This is bromine. A few things should be popping out as you look at this periodic table. First thing I want you to notice is this looks a little different than the symbol that we just showed you. The way that they organize this information on the periodic table is different than the standard symbol that we use to represent the element. On the periodic table, the atomic number is shown on the top. We can tell it has an atomic number of 35. It's also good for you to notice, as we mentioned earlier, that this periodic table is arranged in order of increasing protons. You'll learn in chemistry class that there's a lot of ways that the periodic table is organized, but the number one way, the number one organizing factor, is starting from the lowest number of protons, which is 1. In the left-hand corner, you can see little tiny hydrogen over there in the top left, all the way down to the bottom right-hand side, which would have the maximum number of protons on it. Something else that I'd like you to take a look at is the atomic mass. The atomic mass is shown on the bottom, but I bet you're noticing something kind of weird. Check it out. Here's what's crazy. It's shown as a decimal. A decimal, that doesn't make sense. On the previous slides, we were showing that the atomic mass is the protons and the neutrons. So how in the world did this become a decimal? All right, so now it's time to explain something to you. It's a new vocabulary word, and it's called an isotope. There are different types of bromine. Yes, I know that's crazy. Not all atoms of bromine are identical. What they're doing is they're showing you the average mass of different bromine atoms that are in the world. We call these different atoms of bromine isotopes. So what in the world is an isotope? An isotope is an atom of the same element that happens to have a different number of neutrons. Let me repeat that. Different numbers of neutrons. We mentioned earlier that the protons will never change. The protons are the one thing that you can rely on to identify an element for you. But the neutrons can actually fluctuate. We're going to look at some different examples of isotopes and see if you can see the differences between them. Here's one isotope of bromine. It's showing you in green an atomic mass of 79. And then down on the bottom left, we see that it has an atomic number of 35. In other words, 35 protons. Well, here's another isotope of bromine. This bromine has an atomic mass of 81. Notice we still have 35 protons because all bromine atoms will have 35 protons. Can we break this down and make it look a little bit more understandable in terms of, okay, what happened to the neutrons then? Let's use a cute little chart to stay organized. On the left-hand side, the isotope of bromine that has a mass of 79. It also has 35 protons, as we can tell. If you remember from earlier, if we take the atomic mass and we subtract out the protons, we could find the number of neutrons. Hopefully this makes sense because the protons and the neutrons always add up to the atomic mass. So if we take 79 and we subtract out the 35 protons, woo, there's our 44 neutrons. All right, take a look at the one on the right. This isotope of bromine has a mass of 81. Well, like we said before, all atoms of bromine have 35 protons. If the protons and the neutrons have to add up to 81 in this particular case, let's take the 81, subtract out the 35 protons, and that should give us the number of neutrons. There you go. Taking a look at the number of the neutrons in the bromine on the left, which we call bromine 79, it has 44 neutrons. And if you look at the one on the right, it has 46 neutrons. How about we do another example of an isotope to make sure you feel good about this? This time, we're going to figure out the protons and the neutrons in 3 isotopes of carbon. Here they are. Notice on the top that each of them has a slightly different mass. We've got the first one with a mass of 12, the second one with a mass of 13, and the third one with a mass of 14. By the way, we also call these by their mass names, carbon 12, carbon 13, and carbon 14. Okay, we also can see each of them has an atomic number of 6. That will never change. All atoms of carbon have 6 protons. So we can go ahead and put that in our chart. Well, now let's compare the neutrons. If the protons and the neutrons have to add up to the atomic mass, that means in the first case with carbon 12, there should be 6 neutrons. Carbon 13, therefore, has 7 neutrons, and carbon 14 has 8 neutrons. I'd also like to take a closer look at how carbon is shown on the periodic table. Remember, we were talking about that mass that's a decimal. Take a closer look at that. Isn't it funny that it has an average mass of 12.011? If carbon has 3 different isotopes, and I mentioned that this is an average, why doesn't it have an average that's right in the middle of 12, 13, and 14? Why does the mass that's shown have a number that's 12.011? It almost seems like that's really, really close to carbon 12. Well, as a matter of fact, what's going on is when they do an average mass that goes on the periodic table, they base it on the abundance of each of these isotopes. In other words, they look at all the carbon atoms in the world, And they figure out, well, how many of them are coming from carbon 12 or 13 or 14? And it just so happens that the majority of carbon in the world is carbon 12. 98.9% of all the carbon is carbon 12. A little bit of it is carbon 13, 1.1%. And now you must be wondering, like, hey, shouldn't these percentages be adding up to 100%? Well, you're right. They do add up to 100%. So what that means is the amount of carbon 14 in the world, which, by the way, is unstable, this is a radioactive isotope, is teeny weeny 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 weeny. It is less than 0.01% of all the carbon in the world. So going back to what I was saying before, when we look at those averages on the periodic table, we refer to them as a weighted average, and it's weighed more heavily based on the fact that carbon is mostly carbon 12. Now it's time to practice. I'm going to give you some time here to make sure you can do some of the things that we've been talking about. This is a great time for you to stop the video and pause the video and try to fill in the things that we're looking for. I'm going to guide you along the way, but we're going to do these step by step. You're noticing that I've got 3 elements shown all the way over to the left-hand side. I'm providing their atomic symbol for you, and you're going to figure out everything else that's in this chart for me, okay? Here we go. First of all, I want you to look at the symbols. I've got AU, AR, and CU. Please take out your periodic table and figure out what element I'm referring to by using those symbols. Hopefully you took a moment and paused the video and figured out that AU is gold, AR is argon, and Cu is copper. The second column is overall charge. Okay, so notice that there's no charges shown in the upper right-hand corner of any of these atoms, and that's because I chose neutral atoms to start you off with, and therefore the overall charge is 0 on all 3. This time we're going to focus in on gold. Let's look at just the first row, okay? Based on what you see with the atomic symbol, can you please figure out the atomic mass and the atomic number for this isotope of gold? All right, here's your answers. Atomic mass, 196, atomic number, 79. Your next step, I want you to use these numbers and figure out for me how many protons does this atom have, how many neutrons does this atom have, and how many electrons does this atom have. Take a moment, think about it, and write it in for me. All right, here's our answer. The protons are the same as the atomic number, 79. Neutrons you can figure out by taking the atomic mass and subtracting out the protons and getting 117. And because this is a neutral atom, your positives and negatives should match up and be the same. In other words, the electrons are 79, just like the protons. Now we're going to go a little faster. Please pause the video as you practice this and see if you're getting it right. Let's look at argon. Give me a mass and give me an atomic number, please. Hopefully you wrote in 40 and 18. Now pause the video again and figure out your protons, your neutrons, and your electrons. Hopefully you're getting 18, 22, and 18. Here comes our last row. For copper, take a moment, write down what's the atomic mass, what's the atomic number. Mass is 63, atomic number 29. Last step on this chart, stop the video, take a moment. Can you figure out the protons, the neutrons, and the electrons? Awesome. Hopefully that was some good practice for you for neutral atoms. Let's make it a little wee bit harder now. Let's move on to a couple of examples of ions. Here we go. I've got 3 new symbols for you. Check them out in red, green, and blue. Take your periodic table, find those symbols, figure out what the element is. You could also use the atomic number if that's helpful for you. That also reveals what the element is. All right, we've got chlorine, iron, and arsenic. Next, look at overall charge. Do you see a charge in the upper right-hand corner? If so, write it down in this column. Okay, -1, +2, -3. Now that's going to be important when we start to figure out the electrons. Remember, when we're doing the protons and the electrons, we have to figure out, did we gain electrons or lose electrons? So keep that in mind. Please take a moment, write down the atomic mass and the atomic number for chlorine. Okay, 35 and 17. Next step, do your protons, do your neutrons, do your electrons, and remember, you've got a charged ion. The overall charge is -1. See if you can figure out what happened to the electrons. Did you get it right? The protons should always match up with the atomic number because that can't change. Neutrons we can figure out by taking the mass minus the protons. And finally, if it's a -1, that means we gained 1 electron. We have 18, whereas a neutral atom would have only had 17. So we gained a -1 charge. Moving on to iron. Iron has a +2 charge. Please write down the atomic mass and the atomic number. All right, moving on. We're going to do protons, neutrons, and electrons again. Be careful with your electrons. Make sure you realize there's a +2 charge on this ion. Okay, protons should be easy. Neutrons should be easy. You had to stop for a moment and think about the electrons. If it has a +2 charge, that means we must have lost 2 electrons. If you look at the overall balance here, the nuclear charge is a +26. That's coming from your protons. There's a -24 coming from the 24 electrons circling around the nucleus. When we add those two up, we get a +2 overall. Last one on this chart, take a look at arsenic. Please write down the atomic mass and the atomic number. You should have gotten 75 and 33. Last time, let's do some protons, neutrons, and electrons. On this one, we've got 33 protons. We know that never changes. Neutrons we figured out by subtracting the protons from the mass, but the -3 means in the chemical reaction, we must have gained 3 extra electrons. It's usually 33, but the electrons must have changed to 36 because we have a -3 overall. Here's something that I thought would be fun for you. I want you to try to work backward. I'm going to give you some random information and you're going to see, can I figure out all the stuff that's left blank right now? Let's start with the numbers in red. First thing I would do, I always do my protons first. I think that's the easiest way to start. Your protons and your atomic number are always identical. Atomic mass would come next. Your protons and your neutrons add up to the atomic mass. Add those together. What do you get? A big fat whopping 39. Yes. Overall charge. Compare your protons and your electrons. Protons are positive. Electrons are negative. That means we've got a +1 overall. This is the atom potassium. You can figure that out by looking at the atomic number. Number 19 on the periodic table is potassium. The last blank on the left-hand side, I want the atomic symbol. Give me the symbol, the atomic mass, the atomic number, and the charge. Here you go. Did you get it correct? Very cool. Now we know that we can actually work backwards and build the atomic symbol and do it both directions, okay? So let's try the one in green. If you took my advice, you started off with your protons. Mass is 79. Overall charge, take a look at your protons and your electrons and compare them. Overall charge should be a -2. How do we know that this is selenium? Look at the atomic number. Atomic number 34 is selenium on the periodic table. Now go ahead and build your atomic symbol. What does it look like? It should be looking something like that. Okay, here's your challenge. You're doing the whole blue row by yourself. Take a moment. I want you to do the whole entire thing without my help. Can you do it? Take a moment, pause the video. This is your last one, everybody. Give it everything you got. See if you can do it. Here we go. Ta-da! Atomic number and the electrons ought to be the same exact number, which is 92. There is no charge on this. Neutrons we can figure out, 146. This element is uranium, and I hope you figured out your symbol. It looks just like this. Well, congratulations, everyone. You finished your lesson on subatomic particles. I hope you found it very valuable. I always appreciate you watching these videos, and I hope to see you next time we have a chemistry video. Have a great day, everybody, and thanks for watching. Bye-bye.